So there are 6 possible photons that could be released in this case. So we could have, it was here, it goes down to here, so it loses a photon with that much energy, or it was here and it goes down to here and it could have released that much, or from here all the way to the bottom, that's 3 so far, but it could be here down to here as well, so that's another one. It could be this one down to here, that's another one, now we're up to 5, and lastly, one that's drawn there, which is there from there. And what we're watching is electrons losing energy, so they're at a high energy level, and then this arrow tells me that they're losing energy and going down one level. They are emitting light. They are going down an energy level and emitting light. Okay? So this is an emission spectrum then. So what we're saying is, this is my energy level diagram here, that each individual drop from one energy level to another produces that photon of light, and then we have a few separate ones. So we have one going from here to here, that produces that blue line. This one is a much bigger drop, is a much higher energy level photon. It produces a higher frequency of light. We're over here on the green, or the bluish green kind of area here. And I guess what we should know as well is that when we were looking at the other one, that we had it the reverse way around, where red was at this end and purple was at that end. That's not really very important, it could be anywhere. So in this case, this would be a frequency along the bottom rather than wavelength. Usually a high wavelength would be at the right hand end, so this must be high frequency, low wavelength. It will still be around 700, okay? So each of these levels here represent different levels that they could be on, but also they represent an amount of energy. So we've had n equals 0, n equals 1, n equals 2, and so on, which eventually goes up to n equals infinity, incidentally. So these lines get closer and closer together, and eventually the electron releases enough energy where it actually leaves altogether. That's ionisation. So it got heated so much that the electrons just popped straight off. We've seen that before, actually, even in our cathode electron gun, where the cathode is heated a little bit, the electrons pop off. That's thermoionic emission, where there's just enough heat for it to release from the metal. So that would be a ground state above. When n equals infinity, it leaves, and that we call ionisation. That's not something that really comes up in your papers, though. Okay. So let's continue. Okay, so at this point I'd like to move on and just show you some questions and how they relate to energy levels. So I'm going to go through one or two to show how it relates, and then we will return and look at the opposite way around. So instead of an emission spectrum, we're going to look at an absorption spectrum, and they are different. Okay? Okay, so another a regular question that we get is about absorption spectrum. So let's first explain what those are. So before, when we were looking at gases, we were talking about hot gases. So they are hot and they're emitting light. This is not the same thing at all now. We are on a cold gas. Let's imagine we've got a patch of cold gas, hydrogen maybe. In this case it's hydrogen. And what we're going to do is we're going to shine some light through the hydrogen. On this side, that light would be white light with the whole range of visible light in it. So all of the frequencies are in there somewhere. It's perfect. It's got no gaps. So we've got the red, the blue, all the way through the, you remember Roy G. Biv, every single frequency of light is in there. Every wavelength of light is in there. And then we're going to shine the light all the way through. And we know that hydrogen is colourless, so we wouldn't immediately notice the difference, but if we were to analyse the light that came out the other side, we'd find something peculiar has happened. It might look white to us, but actually it's taken some wavelengths away. So that means that the light here has absorbed some of the light energy, and what's come out the other side is slightly different. So let's take a look at what that looks like. So just as an electron can drop between energy levels, in the case of the hot gas, it's dropping levels because the energy of the electrons are making them slightly less stable. They're more stable when they have less energy, so they release the photons. It's also possible for us to give energy to the electrons that are in that atom, in that gas. So in gases, remember, the particles are really far apart. So they're receiving energy quite separately, these atoms, because they are separate from each other. Now, when I shine a light on them, an atom in there can also jump up a level as well, or more than one level, if the light or if the energy that it's receiving is just perfect. So it has to be just perfect to lift it from one energy level to the next one. Nothing in between will do. If I have not quite enough energy to reach the next level, the atom simply won't absorb it. Okay? So that means that some light, when we shone our white light through our gas, some of it is absorbed, very particular photons are absorbed. And it's only a single photon of that relevant energy can cause it. You can't have it mounting up. It's a bit like our photoelectric effect where we were talking about the particulate nature of light. It has to be just one photon for this to work. So one photon interacts with one electron. It doesn't mount up, it doesn't gradually give it enough, and then it pops up a quantum level. This is, by the way, it mentions in that other video, is the quantum leap, so it's going from one level to the next. It's only possible for a single photon to do this. So it has to be perfectly the right amount. And this is what we get. So this is an absorption, this is an absorption spectrum down here. That's the emission spectrum. This is the absorption spectrum. So when I shine the white light through, I find that there is some missing, and that's because of those photons being taken in. And here, look, there's a dark line. So that dark line there tells me that that particular photon, at that very particular wavelength, that very particular frequency, has been absorbed by something. And of course, it is the electrons within those atoms. And then there are a number of lines, and it's no coincidence. Look, this is the emission spectrum. They are the same wavelengths, of course, because the energy levels are going to be the same in hydrogen. It doesn't matter what hydrogen is, whether it's getting energy or giving it out. So I've got a black line here where I would have had one emitted where an electron in a hot gas is releasing that energy. That's the very same one that it absorbs, which I have right here. Now, when it comes to actually explaining this in papers, which I'll take you through the points when I go through one of the questions for you, they do a bizarre thing. They ask you to explain the black lines. And there is one thing that I find that people would not say, which is for the third mark in that question. So I'll just point it out now. When that white light shines through, the photons are absorbed, just as we said. But afterwards, that electron is, of course, then at a higher level. Just as we explained before, the electrons are less stable when they're at a higher level like that, and so they have to release that energy again. So after they've absorbed that light, they then spit it straight out again. So we'll talk about that when we go through the question.